In these problems, we're going to find the wavelength. To start with, we have an electromagnetic wave, a photon, has frequency of 100 hertz. Find the wavelength. Go ahead and pause and come on back. If you're back, remember that speed of light equals frequency times the wavelength. And so if I know my frequency, 3.00 times 10 to the 8 meters per second for speed of light divided by frequency is going to equal our lambda. Divided by 100 per second. Per second will cancel out. This is divided by 300. My lambda is going to be, divided by 100. My lambda is going to be 3.00 times 10 to the 6 meters, or 3 million meters. This is a very big wave. So 3,000 kilometers between peak. This is very, very broad wavelength. Let's determine some from energy. If we know that there is 4.57 times 10 to the negative 28 joules, can we find the wavelength of that photon? Go ahead and give it a try and come on back. All right, if you're back, remember that energy is equal to hc over lambda. So we can solve lambda if we rearrange so that lambda is hc over energy. 6.626 times 10 to the negative 34 joules seconds. 3 times 10 to the 8 meters per second. And my energy of 4.57 times 10 to the negative 28 joules. What we'll find is that lambda is 434.9 meters. So half a kilometer. Substantially smaller wavelength than our original example, but still huge. Visible light is in the nanometer range, a couple hundred nanometers. So this is 10 to the 9 times larger in wavelength than visible light. Which makes sense, because the energy for visible light is 10 to the negative 19, which is about 9 orders of magnitude higher energy, so I'd need 9 decimal places smaller wavelength. If we have a frequency, we can find a wavelength. If we have energy, we can find wavelength, or vice versa for all of these. These let us jump between the different aspects of how we have to measure and discuss photons.